Okay, well, good afternoon, everybody, and welcome to the second of today's webinars from Smart Vision Europe. In this second webinar, we're looking at Bayesian analysis, and we're looking at how Bayesian analysis is applied within SPSS statistics. Again, if you haven't joined any of these sessions before, you should be aware that these sessions are recorded. So we do record them. And with regard to the slides, it's a fair few slides in this particular one. There's a lot of theory. We'll email out a link to you so you can download the PDF of them afterwards. If you think it's relevant for colleagues who are unable to join, the best thing to do is either just ask us if we need to rerun it by sending us an email, assuming you can get enough people together. Otherwise, just point them at the recording. And with regard to asking questions, all the lines are muted. So I won't be checking the chat panel, but my colleague Rachel is also online, and she'd make sure everybody's logging in correctly. She'll be noting down questions as we go along. We'll probably follow up with you afterwards, which we do after every webinar, or you can send us an email afterwards. It's fine, and we'll follow up with you afterwards and answer your questions then. With regard to who we are Smart Vision Europe, and we are a technology organization. We're gold accredited partner to IBM, as well as Predictive Solutions and a company called Data Robot, who I'll be talking about in the next web session this afternoon. And we specialize in statistics, advanced analytics, AI, machine learning, all that sort of stuff. And we work with original equipment manufacturers, so off-the-shelf analytical tools, as well as open source analytical tools such as R, Python, Spark. We're a relatively small company. We're made up of a team of people who have 15 to 30 years of experience working in the advanced and predictive analytics software industry. And that means we've got very deep experience of applying different types of analytical techniques from different traditions and many different applications across a wide range of public sector and private sectors, including things like retail and water utilities, power utilities, finance and insurance, manufacturing, housing, charities, etc., etc. So against that background, let's talk about where Bayesian fits within the realm of statistical analysis. And this is pretty common. This is a common sort of lecture. You'll get a lot of sort of, stats lectures will kind of spend an hour talking about Bayesian statistics and how it differs from what are known as sort of traditional frequentist statistics. And we can think of this as two separate paradigms. The first paradigm is what's known as the frequentist paradigm. Basically, if you've been taught stats at university, or you've been using statistics in the past, and you've done things like statistical tests and stuff like that, then you're probably working within the frequentist paradigm. You might not have known that, but that's what traditional stats that have been taught in universities and so forth fall within. And the frequentist tradition is has its roots in probably early part of the 20th century. It's got a relatively small number of people who were the major contributors to that tradition, in the sense that they laid down a lot of theory. And the main contributor is R.A. Fisher, Ronald Fisher. So Ronald Fisher, who's kind of like the granddaddy of frequentist statistics. He's the person that came up with the term significance test, for example. He's the person that decided that, well, he didn't actually decide that 5% was a good level. A good 0.05 would be the alpha level at which you reject a null hypothesis if it falls below that point. He just suggested it as one potential alpha level. He also said, well, maybe 1 in 50, or maybe 1 in 100, maybe 1 in 200. Nobody paid attention to that. They just said, all right, 1 in 20 it is, then it's 5%. And as a result of that, thereby hangs a tail, and thereby hangs a lot of heartache, really, further on down the line, of which we'll talk about later on. Carl Pearson was his contemporary. Carl Pearson is the person who's responsible for a lot of the statistics of Pearson. In front of it, Pearson chi-square, Pearson's product moment correlation. They came up with these statistical methods, these statistical tests. Egon Pearson was Carl Pearson's son. So it's all very cozy. Egon Pearson's co-worker was Jerzy Neyman. They came up with things like power analysis and confidence intervals kind of in the 1950s and 60s. So, if you're, if I throw out terms like confidence intervals, F tests, F is for Fisher, chi-square, correlation coefficients, power analysis, null hypothesis, p-values, rejecting or accepting. That's all frequentist, and all of the people, and these are the people who were responsible for that. They didn't necessarily always agree with one another, which is one of the reasons why, for a lot of people, it can be somewhat of it can be a bit inconsistent, I would say, in terms of how people make sense of that particular tradition. Versus the Bayesian approach. The Bayesian approach has become much more fashionable, if that's the term, just a lot more. It's just very hot. It's gaining ground a lot in the machine learning, the AI, and the statistics world, and has been for some time. And that is named after the Reverend Thomas Bayes. Reverend Thomas Bayes was an 18th century philosopher and mathematician. He was actually born in 1701. He wasn't very prolific, didn't write a lot, but his most seminal work was actually just a very short essay that he'd published about I guess about probability, about risk, about trying to assess probability. And it was actually published by his friend, but Richard Price, after his death. So he didn't even, it was just almost like a throwaway piece. Suffice to say, Reverend Bayes would be extremely shocked these days to find that a relatively small essay that he wrote has given rise to an entire field, an entire approach, an entire paradigm of analytics called the Bayesian approach. It turns out that this Bayesian approach, of course, being a serious counterpoint to the frequentist tradition. I mean, statistics didn't really exist in our modern form when Thomas Bayes was around. The whole notion of probability really shows up very late in the day in terms of the history of mathematics. It comes about very, very late in the day. But Bayesian's work was actually, the reason why it became popular was because it was taken up by Pierre-Simon Laplace. And he was a famous mathematician, statistician. He took the Bayesian approach and basically used it to establish new methods for calculating probability. And the Bayesian approach pays great attention to expert knowledge or to pre-existing evidence. This is one of the biggest differences. Well, it's probably the fundamental biggest difference between frequentist and the Bayesian world. Is the Bayesian world incorporates prior knowledge. And that's a complete anathema to frequentist. So why are people really interested in Bayesian? All right, so what? It's a new, it's a new technique, or it's a new approach, or it's a different approach, an alternative to frequentist tradition. Why is it gaining traction now? Well, first of all, you're definitely seeing a lot more interest in it over the last few years. You can easily do a citation search, and you'll see that Bayesian techniques are being mentioned again, and with increasing frequency over the past decade or so, past 2 decades. One of the advances in computing technology, see, one of the things that when Pearson and Fisher were about, one of the things that the frequentist tradition allowed people to do was it allowed people to calculate results and probabilities by hand. And in fact, there was money to be made in that. Carl Pearson made money from publishing books of tables where you could look up things like chi-square statistics and then find out the associated probability. So you could calculate the magic number and then look it up on the table. It would tell you the p-value associated with that. So you could do it by hand. Sometimes it's very laborious, of course, but you could do it by hand. Properly, in proper instances of Bayesian statistics, actually you might require resampling, which is similar to like bootstrapping, and it requires more complex calculation in a lot of occasions when we were trying to apply it in the same way that we would apply, say, a t-test or something like that in frequentist statistics. And as a result of that, it took a while for the computing technology, for the computing power to be around that wasn't a big overhead. I mean, even in the 80s, a lot of statistical procedures on a desktop PC, would have taken a bit of time for them to calculate, and certainly things like memory and computing power was an issue then. It was something that had to be taken into consideration. So Bayesian, as you can see, really starts to take off in the 90s when desktop computing starts to get a bit more powerful. The other thing is that it does have a good reputation for dealing with smaller samples. That's always going to be really popular and really attractive to people. You will see, if you ever do like a chi-square test in SPSS, you'll see the term asymptotic. Asymptotic simply means it means that this type of statistic is most reliable with larger samples. Now, the larger samples might just be 50 cases or something like that, 30, 40, 50 cases, 50 records in each group. But nevertheless, there are plenty of situations where you got very rarely occurring phenomena, and therefore, with the best will in the world, you're not going to get more than 20 examples of something occurring. So that's useful to know that it's got a good reputation for dealing with small samples. Second thing is something called the replication crisis. The replication crisis is a general term that refers to the fact that, particularly in psychology, due to people, Carl Pearson's throwaway remark when he said, a test of significance, you might want to choose an alpha level of about 0.05, 5%, 1 in 20. So many people took him at his word and basically decided that was the level at which you would reject a null hypothesis if the value fell below that. It meant that years later, decades later, when certain famous psychology experiments, particularly, people tried to repeat them, they couldn't replicate the same results. And a lot of the argument around that is that the p-value was too large, that it was too prone to false positives, for people finding effects that didn't exist, and that really we should be thinking more carefully about how we reject a null hypothesis. In other words, finding an effect. So it is a crisis. There are many papers that have effectively been shown effectively to not be true, and that some people have built their careers around that. Flexibility of experimental design. Some experimental designs have a lot of elements to them. If you've ever done anything design of experiments type analysis, it's there can be, it's not always just a case of control and test. You have structures, you have hierarchies, you have more than one control group. Some experiments have quite complex, and it is argued that Bayesian is more flexible in that than Frequentist. Some people say it's actually more intuitive, evidence-based approach to hypothesis testing. As you will see, the Bayesian approach doesn't use a p-value where you reject a null hypothesis. It gives you what's called a ratio, called a Bayes factor. And some people say that this is just a bit more intuitive rather than arbitrarily rejecting a null hypothesis based on the fact that your p-value is 0.02 or something like that. And the last one is it's actually while the statistical community was doing its thing in the 1950s, 60s, 70s, 80s, and 90s, the machine learning data science community was doing its thing, and the two didn't necessarily get on or talk to each other, but the machine learning algorithms were quite happy to incorporate a lot of Bayesian approaches to their workings. And as a result of that, you do hear Bayes mentioned, Bayesian approaches mentioned in a lot of machine learning algorithms. So it's already established effectively within the machine learning community, even if it's only now gaining favor more recently in the statistical community. Okay, so what about the differences between Frequentist and Bayesian? Well, first of all, there are some pretty fundamental differences. In the Frequentist tradition, probabilities are related to how frequently something occurs. If you want to work out whether or not there's something going on, you got to go out there and collect data on it and count how often that occurs. So if you think that there's a certain region of a town where people are more likely to have a respiratory illness and you suspect there's something going on, you need to go out there and collect data on that and say, okay, now how many incidents of respiratory illness are you getting in that region versus the other region? So you basically go and count. In the Bayesian approach, probabilities are related more to the level of certainty or uncertainty of something. That's kind of vague, I know, but that's what it's talking about. That's the kind of background to it. It talks about, you know, it talks about our level of certainty. So it's already talking about our understanding of something. So it's talking about incorporating our understanding of something. In the frequentist tradition, therefore, data is king. And the only thing that you can use to make a decision is data. Whereas in the Bayesian approach, it says data is really important, but so is the context around that. What so is prior research, prior understanding, and what seems reasonable to assume. So it's kind of, so it isn't just so dogmatic to just use data. This is really important. In the frequentist tradition, the parameter is a fixed value. Statistics in the frequentist world is the science of variation, where you're trying to estimate a parameter. A statistic is something comes from a sample. A parameter belongs to a population. So let's say you wanted to work out the level of salinity in the Indian Ocean or whatever, and you decide this is the Indian Ocean, this is the territory around it. You take a sample and you measure the salinity in that. You take another sample, you measure the salinity in that. It's slightly different. You take another sample, you measure the salinity in that, and to 16 decimal places. It's tiny bit different. The idea in the frequentist world is that the average salinity of the Indian Ocean exists out there as a single number. It's just unknown, and you'll just never collect enough samples to estimate it to an infinite degree of decimal places, so that you know exactly what the true number is. In the Bayesian world, it's not a parameter, it's a random variable, it's a zone, it's a distribution where one value is probably the most likely value, but it's only the most likely value. It's not the actual value. It's just the peak of the curve. If you think like the top of a normal distribution or something like that, it's the most likely value. So it's still a random parameter. In the frequentist tradition, the truth is fixed. The parameter is fixed, but the estimation is uncertain. So your estimation, your model may change from one sample to the next, but the truth is fixed. Whereas in the Bayesian world, the truth isn't fixed. It's a random variable. It's in a zone. The estimation is fixed. Your model is fixed. It's kind of like, in the frequentist tradition, it's like you're trying to take a photograph of a bee or something like that with a zoom lens, and the lens is moving around. That's the estimation. It's uncertain, but the bee is sitting still. Whereas in the Bayesian approach, it's that the bee's moving around, but the lens is rock still. So it's a very different approach to trying to uncover the truth. In the frequentist tradition only relates to the null hypothesis. It doesn't say anything about the alternative hypothesis. People make the mistake of saying, when they're doing a significance test in the frequentist tradition, in the classic stats tradition, they make the mistake of saying, "Oh, we've accepted the null hypothesis." You never do that. In the frequentist world, you never accept the null hypothesis. You can only reject it or not reject it. It's entirely one-dimensional. You can never accept the alternative hypothesis. You can never reject the alternative hypothesis. And you can never accept the null hypothesis. The only thing you can do is find enough evidence to reject the null hypothesis. It's totally one-dimensional. Whereas in the Bayesian world, it actually looks at the amount of evidence for the null hypothesis and the alternative hypothesis and weighs one against the other. It uses a ratio field called a Bayes factor. How much weight of evidence is there in the direction of one rather than the other? So that's quite attractive to a lot of people. It only uses the collected data and nothing else in the frequentist tradition. Whereas in the Bayesian tradition, it uses the collected data and an estimate of the truth in the absence of any data. In other words, if you didn't have any data at all, it makes you have an estimate of the truth. And that isn't an optional aspect of the Bayesian world. It actually insists that you give it what's called a prior estimate, what's called a prior probability, before you even collect the data or before you even start to look at the data. So very different approaches. Now, in most cases, of course, particularly most simple analyses, both approaches will yield very, very similar results. You probably won't find that Bayesian completely contradicts the frequentist tradition or vice versa. So bear that in mind. but they are different, and they're often, even if they reach the similar conclusions or the same conclusions. So here's a perfect example. One of the things that's almost like a little game you can play with students of statistics is to get them to talk about confidence intervals. If you actually Google correct way to interpret confidence intervals, if you actually Google that, I think to this day, the first hit you get is incorrect. And the interpretation of interpreting confidence intervals is actually wrong. It's actually giving a Bayesian interpretation. And let's talk about that. So in the Frequentist tradition, it basically says, if we were to repeat the analysis many times, 95% of the computed confidence intervals would contain the true value. That is not the same as saying that based on our data, there is a 95% probability that the parameter lies within this region, within the confidence intervals. That's actually what Bayesian statistics do. So in the Frequentist statistics, what it's saying is you can be 95% sure of the technique, but the true value is kind of unknown. It's not, you can't say anything about the 95% probability of true value. And that makes sense because we've kind of just talked about that. If you look at it, the Frequentist tradition, the bit that's variable is the confidence intervals. They vary from one sample to the next, but the true value is fixed. Whereas in the Bayesian world, it says the intervals I'm giving you, what it calls credible intervals as opposed to confidence intervals, pretty much interpreted in a very similar way. But here in the Bayesian world, we say that there is a 95% probability that the parameter lies within the credible region. So that's variable. So, the model is variable in the Frequentist tradition. The parameter is fixed. In the Bayesian tradition, the model is fixed. The estimates are fixed. But the parameter itself is variable. That's a zone that you're trying to find. Very different approach. Different approach to it. So as a result of that, a lot of people find that Bayesian credible intervals are much easier for people to interpret and work with. So they just make sense. It's because you can say, oh look, what do those two numbers mean? It means that there's a 95% probability that the true number lies within that region. And people say, oh yeah, I get that. You can't say that with classic Frequentist statistics. And that's why during the pandemic, when you look at government statistics on things like the R number, that's the rate at which a coronavirus was spreading, whether it was above 1 or below 1, it often didn't give confidence intervals, it gave credible intervals. And that's because the statisticians such as David Spiegelhalter behind that, knew full well that politicians could at least correctly interpret credible intervals, but they were very likely to get confused over confidence intervals because most people get confused over confidence intervals. If you get confused over confidence intervals, you're in very good company. Okay, what about this business of having information before you even collect data? This is in the world of Bayesian, the Bayesian world, this is called prior and posterior probabilities. So you remember here, the Frequentist tradition does not use prior probabilities, only uses collected data, whereas the Bayesian tradition uses collected data and an estimate of the truth in the absence of any data. So in other words, it includes the calculation of prior probabilities, the probability of an event occurring, or the probability of a value being true, or a certain range, based upon established knowledge or beliefs. That is easily, the most controversial aspect of it from a Frequentist point of view. But if you think about it, if you take it to its logical conclusion and think about the most simple example you can think of, which is what's the probability of the coin landing heads, and you're about to flip a coin. Technically speaking, in the Frequentist tradition, if you didn't know anything about the coin and you've never seen this coin before, maybe it's from a country you've never tried before, technically speaking, if you were trying to figure out whether or not it was a fair coin, the Frequentist tradition technically saying, well, the probability could be anything. Could be 1 in 10,000 that you're going to get a heads. It could be 100% true that you're going to get a heads, 99%. It could be 10%. It could be 5%. It could be 50%. But that may not seem very reasonable, but that's what the Frequentist tradition says. It says, you got to go off and test it. You got to collect data on it. flip it 10 times, flip it 50 times, flip it 100 times, and count up the frequency. Whereas the Bayesian tradition says, you know, look, there's two outcomes here, and the coin looks fair. We might want to at least start and assume that the initial prior probability is 0.05, and then we can update this prior probability with the data that we collect after we flipped it 10, 15, 20, 30, 40, 50 times. So it's a very different approach. And that's the context, if you like, and how the context provides a prior probability for us. In Bayesian statistics, the prior probability is a probability distribution that would describe the likelihood of a given value before some new evidence is taken into account. Okay. As such, those working in the frequentist tradition have often regarded this idea as the most controversial aspect of the Bayesian approach. Of course they do. That's hardly surprising. The prior could be the expected proportion of people likely to vote in a referendum, for example. Likewise, it could refer to the expected mean and standard deviation of an age distribution describing when people get married. It's kind of a rough guess. The frequentist tradition would say, look, they might get married at the age of 2, and they might get married on average at the age of 99. The Bayesian tradition says, look, I mean, come on, let's be reasonable. Let's assume it's like, average age is 28 or something like that, and the standard deviation is 10 or something, or 8 or something like that. It makes some sort of rough guess. These prior probabilities could be based on past research, subject matter expertise, or reasonable assumptions based on the context of the study. So prior probabilities, let's talk about them in detail a wee bit here, because you will, if you start to look at Bayesian stats, you will see these terms starting to pop up. And I don't want to get into it in too much detail, but I need to explain what they refer to. There are going to be situations where you just don't have any information at all. You've just got no idea. The value could be anything. And in which case, that's called an uninformative prior, and it means effectively it's very close to a frequentist stance. It says there's a equal chance of the value being anything. It's equal chance that the average age could be anything from 1 to 101. That's what it is. That's an uninformative prior. Examples include probabilities where every outcome is equally likely. If the prior and the posterior probabilities, however, come from the same statistical distribution family, now, if you're not used to thinking in those terms, when you do a statistical test like a binomial test, that refers to a statistical distribution called the binomial test. If you're doing an F test, that's referring to an F distribution. You've got a normal distribution, you've got a gamma distribution, you've got Weibull distributions. Most classical statistics are just collections of distributions for different situations. For comparing two averages, that's a T distribution. For comparing differences in proportions, might be a chi distribution. For comparing the number of times an event occurs, might be a hypergeometric distribution. And these tests that we run to try and compare these groups, or try to compare data in these situations, make use of those distributions. So for example, if you were flipping a coin, you say, look, if the prior distribution is binomial and the posterior distribution also binomial, then we call those conjugate distributions. And the prior is called the conjugate prior. It means that the prior distribution, the prior probability, however that's described, however it maps itself out as a curve, matches the probability or the distribution that comes out after you've done the analysis. That's called the posterior. And the major criticism of Bayesian approaches is that there is no single prescribed and well-defined method for choosing a prior. This is a big issue. Using different priors for the same problem can mean that analysts reach different conclusions. That being said, some people actually think of that as an advantage, because it means that they can play around and do what-if analysis and say, well, let's assume the prior distribution looks like this. It's not normally distributed. It's a little bit skewed in one direction, so maybe it's more like a skewed distribution, like a Poisson distribution or something like that. How does that affect things? But it is dependent on that to a certain degree. And if you don't have any information about that, or if all previous studies have been wrong, which is entirely possible, I think that's probably why a lot of frequentists, it gives them hives, why it makes them so scared, is that, you could end up incorporating information from completely, false studies that, that are basically that have been incorrect. So that's a few things. So there's the prior probability. You saw me mention the posterior probability. That just refers to the probability that results from updating the prior probability of the new evidence. It's what comes out. It's the result of your analysis once you've incorporated the data and you've incorporated the prior probability. And this new evidence usually takes the form of collected data and is often referred to as the likelihood function. So when you hear them talking about terms like likelihood function, they're usually referring to the data. The posterior probability is therefore the prior probability incorporating the new evidence, incorporating the data. So it's what comes out. It's your updated value. After you've said, look, I think this coin's fair. My prior probability I'm going to assume is 0.5. Now I'm going to flip the coin 100 times. It comes up 60 times heads and 40 times tails. I'm going to combine these two values together in some way. It's not just a case of just multiplying one by the other, but I'm going to combine these values together in some way to create a posterior probability where I combine my prior assumption with the new evidence to make an estimate as to the probability that the coin is fair. Okay, which leads us to the thing that Bayes actually talked about, the paper that he actually mentioned. It was a way of calculating a probability, and this was known as Bayes' theorem. Okay, so Bayes' theorem is based on what's called Bayes' rule, and Bayes' rule has a couple of elements within it. So just to explain what this, we're going to see a little bit of formula here. What is that? What are we going to be shown? H means the hypothesis, and I'm going to assume you're familiar with a hypothesis, a null hypothesis or an alternative hypothesis, a hunch, a statement. Is the coin fair? Is the average age that people get married at close to 28 or something like that? Some new evidence, some data that you've collected, that's E, some data that you've collected. And that means the probability of H given E. So if you see this vertical bar in this sort of, these types of formula, it means given or assuming. So the probability of the hypothesis being true given the evidence, which is what we're trying to figure out, of course, when we do a statistical test, that's our result, is based on the probability of the hypothesis being true to begin with, that's your prior, and the probability of the evidence given the hypothesis. So I'm going to have a walk through this, but notice that this bit here is the opposite of this bit. When you do a Frequentist test and you get a p-value at a Frequentist test, that's what you're getting out of a Frequentist test. A classic. If you do something like a chi-square test, what it's showing you is the probability of getting a result as extreme as the one observed. That's the probability of that evidence, assuming that the null hypothesis is true, given the null hypothesis. So it's the probability of getting that result in a universe, if you like, where the null hypothesis is true. So that's what a Frequentist p-value actually is. And that's divided by the probability of the evidence. So it's probability of the hypothesis times the probability of the evidence given the hypothesis divided by the probability of the evidence. Now, I completely accept that the first time you've ever seen that, if that is the first time you've seen it, that's completely abstract. So therefore, we need to have a little example. And in many ways, this little example is just a worked example where we're going to take that apart, where one is the probability hypothesis being true given the evidence, that's the thing we're trying to calculate, is based on the prior probability of the hypothesis being true. That's our prior probability. Like this is when we say 0.5, we think this coin is 0.5. And then we're going to flip the coin 100 times, for example, and I'm going to see it comes up 60 times heads and 40 times tails. So we're saying, what's the probability of getting a result as extreme as that, 60-40, if we assume this coin is fair, divided by the last bit, which is the prior probability of the evidence being true, which is what's the likelihood of getting that result? With the prior, how often do you get a result just as extreme as that, irrespective of whether or not the evidence is true? So what does that look like as a little example? Well, here's a little example that we've got. Bernie thinks his metal detector has found a hoard of Saxon gold. Okay, so that's what we're trying to think. We're trying to figure this out. he's got a really strong signal. He hasn't seen that before. It's pretty rare to get something like that. And he's out in a field in Norfolk, and he knows that there's been other hoards found around it. What's the probability that he's actually found gold? Well, we're going to incorporate these different elements, and it's almost like a back of a sort of beer mat calculation that we're doing. And it looks like this. So it's like P, the prior probability of finding gold. That's like, how often does that actually happen? That's P equals H. Turns out that's like 1 in 10,000 times people find gold in a given session, 1 in 10,000 sessions. What's the probability of getting that signal if it was gold? How reliable is that signal? Well, it turns out it's reasonably reliable, 75%. If you put it over a lump of gold down there and it's 4 foot down, it turns out that 75%, if you get a signal as strong as that, it turns out it usually is gold. And last one, the probability of getting a strong signal, the probability of actually getting that signal. How often do you get that? Well, it turns out, you get that, 1 in 500 times. So you don't really see that signal very often. So that calculation then becomes effectively this 0.001 multiplied by 0.75 divided by 1 in 500, which is 0.002. And that means you get a probability value out there of about 3.75%. So is it likely he's found gold? Probably not. Now, this is the posterior probability that we're calculating. And we've incorporated some prior probability with some evidence that we've collected in order to get this value. If you change these numbers around, of course, you're going to get a different posterior probability. But this is how Bayes' theorem is used in a practical example. So let's talk about how we actually do tests and stuff like that. How do we find out things with what does that look like in when we're applying Bayesian analytics? Well, in the previous example, we introduced the fundamental principles of Bayesian analysis using Bayes' theorem. In particular, we saw how Bayes' theorem can combine evidence from new data, the likelihood, and the prior probabilities to provide a posterior probability. The population parameters, however, that we might be trying to estimate aren't just things like means and proportions, but they're usually things like the difference between two means, such as, you want to find out if the difference, say left-handed people have a different blood pressure from right-handed people. So, you're looking at the mean left-handed, the blood pressure for left-handed people and the mean blood pressure for right-handed people. What you're really focusing on, of course, is the difference between those two means. And if it's a big difference, and if it's got a decent sample size, you're going to go, wow, that's quite notable. I wonder what the probability is of getting a difference that big. Or you might be looking at the proportional differences between the voting habits of different ethnicities. So you're saying, okay, look, people in this ethnic group vote X% in that political direction, whereas people in this ethnic group only vote about Y% for that particular political direction. Or the correlation between travel distance and shopping frequency. You think, okay, the further away you are, the less likely you are to shop. They're still going to get a negative correlation. But, you want to know if that's just this correlation value you're getting is to use the dreadful term statistically significant or not. So these are the things we're trying to understand. In Bayesian analysis, we estimate a parameter's posterior distribution by combining a prior distribution of the likelihood obtained from the data. This is what we've already established. Specifying a prior distribution is an important aspect of this process. We've established that as well. Bayesian analysis will return a mean estimate of the parameter value, such as the mean difference or the mean correlation. But really, as Bayesian analysis sees the parameter as a distribution of values reflecting the uncertainty, analysts focus on the credible intervals that encapsulate 95% of this distribution. So here we get to the nub of it. Credible intervals are the Bayesian equivalent of confidence intervals, except that here we can say there's a 95% probability that the parameter lies within these bounds. So that means that if the credible intervals estimated a range of values that related to some sort of difference between groups, and if we find that that difference contained two intervals or two credible intervals where one was a minus number, the difference was lower in one part of it, and was a positive number in the other part of it, well, that would mean obviously that the difference contained a zero, that the range contained a zero, which means that, of course, there probably isn't an effect because it could be anywhere from the negative number to the positive number. So in the SPSS output below, we can see using Bayesian credible intervals, here we are comparing two groups. We're saying, I want to compare the mean previous experience in months for clerical workers and managers. I've got 84 managers. I've got 364 clerical workers. Here's the mean number of years of experience, months of experience for clerical workers is 85 months. Managers 77 months. I mean, it's it's a decent enough difference. It's not tiny. It's about it's a bit less than seven months, but it's there. And when we calculate our credible intervals, it says, well, the mean difference is minus 7.42. That's the difference between these two values here. And it says, okay, let's calculate the credible intervals. It's saying that based upon these data here, and based upon our priors that we've put in there at some point, put in a non-informative prior, it turns out, this difference could be as low as minus 26 months or as high as 11 months. So minus 26 to 11 months. So that means that the difference could be zero, doesn't it? There's 95% chance that the difference could be anywhere between these 2 points. That's the same as saying, that we kind of we can't reject the null hypothesis, and we haven't found an effect in this. So that's one way in which we can do a statistical test, if you like, using Bayesian statistics, just by using the credible intervals and looking to see if there's if the difference or the relationship we're observing goes from a minus number to a positive number and contains or encapsulates a zero within it. And if it does, then it means that the possible difference or the possible relationship, the possible correlation, if you like, could be as small as zero. Okay. In other words, there's not much evidence that one group has more previous experience than the other. Okay, what about this other approach that Bayes has, this Bayes factor approach? It's actually got two things up its sleeve, which is hypotheses. We haven't said anything about hypotheses there. All we've done is we've just compared, we've created credible intervals, and we've sort of said, look, is this difference likely to be a negative difference? Is it likely to be a positive difference? And if it's a negative and a positive, then we're saying it's possible that it could be zero difference. In statistical inference, there is an important difference between estimating a population parameter, such as trying to estimate what the average value is, which we tend to use confidence intervals for and credible intervals for in Bayesian statistics, and testing hypotheses about it. They are separate things. In the previous example, we looked at how Bayesian estimations attempt to approximate a parameter's posterior distribution. Now we turn our attention to testing hypotheses using Bayes factor in the same way that we might do using a frequentist p-value. In the frequentist approach to inference, much attention is focused on the null hypothesis. Remember, we're always talking about, can we reject the null hypothesis? When the p-value is calculated and found to be lower than a pre-specified alpha level, such as 0.05, the convention is to reject the null hypothesis. What we can't do with this information in the frequentist world is use it to accept the alternative hypothesis. This test simply doesn't consider this condition. It's purely one-dimensional. However, so what happens when the result is non-significant, such as p equals 0.38? All that happens is that the null hypothesis is not rejected. As such, the frequentist approach has very little to say about evidence for one hypothesis versus another. So whereas a p-value is used to reject or not reject a null hypothesis, it turns out the Bayes factor compares the evidence for separate hypotheses by dividing one by the other. In SPSS, the resultant ratio of evidence attempts to quantify how much more evidence there is for one hypothesis versus the alternative hypothesis, the null versus alternative. So it's immediately we're suddenly starting to talk about the alternative hypothesis, which we never do in the frequentist world. And by doing so, it compares the evidence for both hypotheses, which is something that frequentist p-value does not do. So this is just labeled B, and it looks like this: to indicate the relative strength of evidence for two theories. These are simply ratios comparing evidence for the alternative and null hypothesis. For example, a Bayes factor comparing a null hypothesis to the alternative hypothesis would show that the data are B times more likely under the null than under the alternative. And because the B value is a ratio, it can range from 0 to infinity. But a value of 1 would indicate that there is exactly the same evidence for the null hypothesis as there is for the alternative hypothesis. That would be, you know, that is one where you're saying there's absolutely equal evidence in both directions. Values greater than 1 indicate increasing evidence for one theory over the other. Example, the null over that alternative hypothesis. And values less than 1, the opposite, increasing evidence for the alternative over the null hypothesis. You notice I'm using example here. And that, unfortunately, is because depending on what method you're using and what tool you're using, sometimes it's labeled BF01 or BF10, where the null is divided by the alternative, or alternatively, when the alternative is divided by the null. You'd think that they would have got together and kind of decided what the convention was, but they didn't. So you need to know, you kind of need to check and just and make sure that you're interpreting it correctly by using the help system or something like that. Whichever tool you're using is not just SPSS. So BF10 referred to situations where the evidence for the alternative hypothesis is divided by evidence for the null hypothesis. In such situations, larger values would indicate more evidence for the alternative hypothesis. Conversely, BF01 referred to situations where evidence for the null hypothesis is divided by evidence for the alternative hypothesis. In such situations, larger values indicate more evidence for the null hypothesis. Rather confusingly, SPSS uses both methods depending on the test. So t-tests, for example, use this method, but the one-way ANOVA uses that method. And I would suggest that you just simply click on the help system when you're using it, and it will give you a little table for that test showing you how to interpret it. So, for example, this is the table for BF01. This is what you'll get if you do like a t-test. And I've shaded it here on purpose. It's actually all one table in the help system, but I've broken it up. And it says basically if the BF value, if the B value is greater than 100, that means extreme evidence for the null hypothesis. That's H0, meaning that there's no relationship. And if it's down to 3 to 10, if you get a value like 5, then it means moderate evidence for the null hypothesis, because it means it's about 3 to 5 times or 3 to 10 times more evidence for the null than there is for the alternative. And obviously, if it gets to 1, then that means no evidence. And as it starts to get below 1, as you get into 1 divided by 3, so a third, or 1 divided by 10, from a third to a 10, so that's 0.33 to 0.1, moderate evidence for the alternative hypothesis. If you get really small values, where it's, 1/30th to 1/10, so, a 1/100th to 1/30th, so you're getting down to like, really small numbers here, 100th, 0.01, right down to over 100th, you get extreme evidence. So the smaller the number, once you get down into real small numbers, you get extreme evidence, or strong evidence for the alternative hypothesis. Okay, so in SPSS, larger Bayes factors indicate more evidence for the null hypothesis. It should be noted that in other analytical programs, the opposite interpretation is made. The above table from the SPSS help system is provided to give users some guidance as how to interpret the Bayes factor and the strength of evidence, null, H0, versus alternative, H1. That's how it's labeled. So here I have an example here using analytical example. This is me doing a kind of a t-test using a Bayesian t-test. Note that the Bayes factor is 8.441. It provides moderate evidence for the null hypothesis. It provides moderate evidence for the null hypothesis that there's no difference in the average amount of previous experience for clerical and managerial workers. Well, we saw that, of course, when we looked at the mean differences, and it gave us the credible intervals that we got a positive number and a negative number. So we're saying that the mean difference could be 0. The Bayes factor here is 8.441. Remember where that is. That's there. It's between 3 to 10. Moderate evidence for the null hypothesis. So this is one of the things it gives us kind of level of subtlety that we don't really get from a frequentist tradition, where you just either reject the null hypothesis or you don't. It's actually saying, the degree of evidence. So you can't really say in a frequentist test, oh, it's very significant. No such thing as very significant. You just have a level. It either falls below that level or it's above it. It's like saying very dead. Whereas with Bayes, you can talk about how much evidence there is for the null hypothesis versus the alternative. And that's one of the things that makes it so popular. Now, notice here that it does actually give you a frequentist significance test. It's almost like they couldn't quite bring themselves to just do Bayes factor. And the frequentist significance test here has a p-value of 0.5042, a 504. So it's you know, they agree with one another. If you did a t-test, it would come out something kind of similar to that, and you would not reject the null hypothesis. Okay, let's have a little look at that. Let me just skip out to SPSS here, and we'll just show you where you can get that. Sorry, I'm just skipping out here. So there we go. So this is the same data set. Where do I find this? I go to Analyze, and I go down to Bayesian Statistics. And because it's a parametric test, the equivalent of parametric test, it's independent samples normal is the equivalent to compare means independent samples t-test, because independent samples t-test kind of assumes a normal distribution. But with most t-tests, that this is easily, most t-tests are quite, you know, they're pretty robust. As soon as the sample size gets above like 30 or 40, it's pretty robust to distributions which are non-normal. So you don't have to worry about that too much if you've got decent sample size. And the same sense here, if I go independent samples normal, similar sort of thing. So here I'm going to pick up the thing that you saw earlier on, which was where we were comparing previous experience in months, and we're comparing that by employment category. So I'm putting that in there. There's my employment category, which is clerical versus manager. Those are the two groups I'm looking at. The only reason I'm leaving out the one in the middle here is because the middle group is custodial. There just aren't very many cases for that. And you can see here the default is to characterize the posterior distribution. What does that mean? If I click that, it basically gives me, if I run that, it basically gives you the credible intervals that we saw earlier on. We can see these credible intervals. It's saying the mean lower bound is -25, upper bound is 11. It could be anywhere between 26 to 11. And would say, look, whatever this true mean is, it could be anywhere in there. It could be 0. And it's actually showing us little charts here as well. So these little charts are showing us the log likelihood and the likelihood. It's basically showing us what the distribution looks like for the mean clerical worker. See, the mean clerical worker here is what's that? 84.94, so it's about 85. If you actually look at where the peak of that is, it's about 84. Whereas for the managers here, it's just a wee bit shifted, 77, teeny bit shifted if you had really good eyesight. And you can see the prior distribution here is just flat. That means that the default position is that it doesn't assume any difference between the two groups. It's giving it a non-informative prior. And then the posterior distribution says, okay, look, this is what I think what the mean difference could be. It could be anywhere between minus, say, 26 to up to 11. And 95% of the data falls within that zone. There's about, let's say 95% of data is there. That's the bottom 2.5%, the top 2.5% here. So it's coming in about 11 here and there. So you can see that's where it's getting these two numbers from. This is the posterior distribution. If I ran it again, I could ask for the estimate the Bayes factor instead and click that. And here the Bayes factor is, what is it? It's 8.486, just what we saw earlier. Significance test saying moderate evidence for the null hypothesis being true. And if you click on up here and you say, okay, do both methods, then it gives you the credible intervals plus the Bayes factor. At this stage, if you wanted to play around with the prior probabilities, you could go into the criteria here. Sorry, you could go into the priors here, and you could play around with that. Now, the first thing you get is it assumes that both groups have equal variation. Sorry, assumes they both have unequal variation. It's being quite conservative. It's saying, look, I don't know. This is a thing that t-tests also do. They actually give you two t-test values. They give you equal variance and unequal variance responses. But you could say equal variance. I'm going to assume they both got equal variance. Does that change things somewhat? 29 to 14. No, it doesn't really change things. What about the Bayes factor? It's still 8.4. It doesn't really change things. Whether you assume they have equal variation in both groups or not. If I go into priors here, I could go into the variance itself. And say, well, I'm going to tell you what group 1's variance is and what group 2's variance is. Now you can actually see here that the standard deviation, you can see the variance here. This is the difference in the variance here. So I think if I put in the variance, I wish it would. I mean, it'd be much better, of course, if if it said, can you put in the standard deviation, then the variance, the variance is the square of the standard deviation. So it's usually a pretty big number. It'd be much easier if it just put in standard deviation, but it doesn't do that. So I'm going to put in 10,000 for group 1, and then slightly less variance for group 2, 6,000. I'm going to say just play around with that to square the standard deviation for these two groups. Does that make a difference? Well, what you notice is that these charts here change because now I'm telling it what the variance is rather than it estimating it from the data. I'm literally saying, never mind the mean. I'm going to tell you, never mind these standard deviations here. I'm going to actually tell you what the variance is for these groups. Does that change things? Well, it's still minus 26 to 12. So no. And what's the Bayes factor? Amazingly enough, it doesn't change it. What happens if I go and change the priors now? The actual priors. So this is the variance of the data. What happens if I change the priors? Well, priors in the normal distribution here, you have what's called the location and the scale. That basically means the mean and the standard deviation. So I can say the means for group 1 is 80 and the standard deviation for group 2 is 75. And the standard deviation is for group 1 is 90 and for group 2 is, I'm going to say 75 again, something like that. I'm just playing around with it. Does that change things? Well, now you can see that the prior distribution is no longer a non-informative distribution. It's actually taking into consideration the prior. What's happening now? Well, again, minus 22 to 0.7. So although the bounds are a bit closer together, Bayes factor hasn't changed at all. We're still concluding things in a similar way. The data really does have quite a strong effect upon it here. You really have to play around with the numbers quite a lot in order for it to have an effect. But that's one example. Note that there are many other types of Bayesian analysis we could do here. We could do one sample binomial. That's your test of a coin. One sample Poisson. So it's more like a count data. We have Pearson correlations. We have linear regression, one-way ANOVA, log linear models, and repeated measures ANOVA. So a Bayesian equivalent for each of these different approaches. Okay. The last thing I would say here is basically there's a very good book I recommend that introduces people to the notion of Bayesian statistics, but also near the last chapters as it really builds up, The Art of Statistics by David Spiegelhalter. Really good book on statistics, generally speaking. Starts with assuming very little or no knowledge of statistics. Very, very clear. And just be aware that in terms of the consultancy services we provide consultancy for project support, analytics advice, and analytical deep dive of different sizes, 1 to 2 days, 3 to 5 days, that kind of thing, right up to multiple days of consultancy. And we also provide help sourcing software, training, consulting, and technical support. I do hope you found that useful. In the meantime, if you want to log in again, we have another webinar coming up in an hour's time. We're looking at data robot, and we have recordings of all of our previous webinars, both on YouTube and on our website. So you might want to check those out. In the meantime, we look forward to you logging in again in the near future. Thank you.